Okay, let's say we have four integers a, b, c, and m, and it's satisfying the following conditions. M is positive, and d is a greatest common divisor of c and m, and AC is congruent to BC modulo m. Then it looks like we can cancel out this c from both sides, but with one condition. Our modularity number is not m anymore. It should be m over d. One thing is clear, d is the greatest common divisor of c and m, so m over d is also an integer, so it's okay to write down this way. So let's just prove it. Let's start with AC is congruent to BC modulo m, which means m is a divisor of AC minus BC by the definition. But let's change AC minus BC to C times A minus B. Same thing, so m is a divisor of C times A minus B, which means C times A minus B is a multiple of m. So for some integer k, we can say C times A minus B equals mk. Let's divide both sides by d, and let's put d under c and m in each side. Then this equality changed to c over d times a minus b equals m over d times k. And because d is the greatest common divisor of c and m, c over d is an integer and m over d is an also integer. And if this is a general case, then clearly m over d is a divisor of this left hand side, which is a multiple of two integers like that. Then we don't know whether m over d is a divisor of one of them, because it shares the divisors of each of them to make m over d. Okay? But since d is the greatest common divisor of c and m, the greatest common divisor of c over d and m over d is actually 1, which means between these two integers c over d and m over d, there is no common divisor except 1. So if m over d is a divisor of this whole number, which is product of c over d and a minus b, then m over d must be a divisor of a minus b, because there is no common divisor between these two. Okay, so we can say m over d is a divisor of a minus b because of that condition, which means, yes, by the definition, a is congruent to b modulo m over d. So from now on, whenever we have two composite numbers having some kind of common divisor like that, c modulo m, then actually we can cancel out this common divisor c from both sides, remaining a and b only. But whenever you do that, you have to change this number m to m over d, which is d is the greatest common divisor of c and m. So what happens if d is 1? Then from this we got this corollary. If c and m is 1, then from this condition we can say a is congruent to b by the same modular m, because actually this is m over 1, but which is m.